times 10 to the power 6 Pascal. Now, I'm going to do another extra point, okay? And there are two ways of solving it, okay? So now I want to find the first moment of, the stress at the centroid. And we know that the stress at the centroid for this case will be at its maximum, okay? So let's do this again. Okay, there's something I want to show you that is important down here, okay? So what we are going to do now is we are going to determine the shear stress at the centroid. Okay? So I'm going to introduce a new point I call point C. Okay, and this is our global centroid. So there are two ways of doing this. Okay, you can find, okay, you can find. So we are going to use either the top section or the bottom section. The answer will be the same. Okay, and I'm going to show it to you. A big thing about this topic over here is confidence. You need to. So if we are going to use the top section, right? So let's consider the top section. So for the top section, right, the summation of the Q at point C will be the Q of the flange plus by the Q the web. Okay, so the Q of the flange, which we already determine, is equal to 160 with depth is equal to 20. Y bar is equal to 35 minus by 20 divided by 2, right? Because the distance from here to here, we know is 35. Okay. Then Q of the web plus by twice. Okay. The width is 20. The depth now is 15. How I get 15? Because the distance from here to here is 15, right? And then the Y bar is equal to 15 divided by 2. Okay, so this will be equal to 160 times 20 times by 35 minus by 10 and plus by 2 times by 20 times by 15 times by 15 divided by 2. The Y bar is 84.5 times 10 to the power 3 millimeter cube, or 84.5 times 10 to the power minus 6 meter cube. Then we can immediately find the shear stress XY at point C. Okay, and this is again 90 times 10 to the power 3 divided by 5.813 times 10 to the power minus 6. This will be equal to 84.5 times 10 to the power minus 6. And then the thickness will be twice 0.02, left and right. Okay. So 90 power 3 times by 84.5 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 0.02 is equal to 32.706 or 707 times 10 to the power 6 Pascal. Okay. Now, what if now we apply, we focus on the bottom section? Right. So what we have done earlier is we look at the top section, right? Right. Then the next one, when I say bottom, we are just going to take the, hold on, wrong color. We are just going to use this area over here. Okay, that I'm shading in blue now. I hope you can see my shading in blue. Okay, so this is for bottom section, right? And then the one in yellow is for the top section. And the answer should be the same. Okay, because the centroid is determined about where we find the global centroid, means the cross-sectional area at the top and the cross-sectional area at the bottom are the same. Okay, the numbers can be different, or how we get there can be different. Okay, so we do summation of Q, right, at point C. Now is twice Q of the web in the bottom, right? So twice the width is equal to 20. The depth is equal to, so we know that this depth from here to here is 65, right? And then it's 65 divided by 2, the y bar. So this will be equal to 2 times 20 times 65 times 65 divided by 2 is equal to 84.5 times 10 to the power 3 millimeter cube, right? Millimeter cube, or 84.5 times 10 to the power minus 6 meter cube. And you have seen this value before. Hey, Eugene, come on. You have seen this value before. This value over here is exactly the same as, come on, as the value over here. Okay. And if you plug in, the answer will still be the same. Okay. So this expression over here is the same for the top and for the bottom, because the first moment of area are exactly the same, right? So I want you to have the confidence, right? And this is because we apply the four rules, right? The first moment of area cannot cross the centroid, and the analysis direction starts from furthest away from the centroid. So this is the analysis direction, and this is also the analysis direction. Okay? That's why whether you find from the top and the bottom, the answer is the same. I will use from the bottom because it has less component. Less component means less what? Mistake. Yes or no? Okay. So the next thing that I'm going to do is we are going to determine the shear stress distribution equation. Okay. So the next thing that we're going to determine, let me get rid of this. Don't need this. Don't need this. We're going to find, and okay, I'm going to write this down first. We are going to determine the shear stress distribution equation. Okay. So why I do this is so that you will know how to apply the 5 rules. Okay. Okay. So now we are going to determine the shear stress equation. Okay. So we know that I'm going to sketch our global centroid over here. Okay. That is our, let me increase the size of this diagram. I think it will help us a lot. Okay. So this is the global centroid. Okay. So we are aware that the distance from here to here is 35 millimeters. Okay. So we are going to determine the shear stress distribution of the fledge. Okay. So the limit in terms of y is 35 or 20 millimeters. Y and 35 millimeters. So this equation that we are going to derive have that limit. Okay, it's only valid from 20 to 35 millimeters. And why 20 to 35? Because over here, the centroid is the datum. Yes? Okay. So from here, if we are interested in a line or at a certain location, so this is our distance that I'm interested in. So this is my y. Okay. And then we are aware that a certain distance from there over here I'm trying to position this that's equal at the top and bottom, and it's not easy. Okay, this distance from here to here is our y bar. Okay, so that's what we are trying to do now. Okay, so now we know that qz as a function of y is equal to width multiplied by depth multiplied by y bar. Okay, so this is the defined area, right? That is our defined area. So to write this out, the width is a constant, right? So the width is 0.16. The depth is equal to 0.035 minus y multiplied by 0.035 plus y multiplied by half. Okay, multiply. So some of you, hey, how come you can write that expression so quickly? Okay, so you have seen this expression before because the expression is what we derived earlier. If we come over here, right, we found our area. Okay, so if I'm going to copy this equation and I'm going to bring it down here, right? So the area is the width, C is the maximum distance, right? So this is our from here our C is this distance, which is equal to 0.035, right? The y is our variable, and then our y bar, right? So we did derive our y bar before. Our y bar is this, right? So this is our formula for our y bar, right? So C is equal to 0.035. Okay, that's why I could write this out pretty quickly. Okay, so from here, this will be equal to 0.08 multiplied by 0.035 squared, which is 1.225 times 10 to the power of minus 3 minus by y squared. Okay, so this is the first moment of area of the fledge, okay, which is a variable. Okay, then when we incorporate everything in, So I put in the 0.08 times by 1.225 power minus 3. We get 98 times 10 to the power minus 6 minus by 0.08 y squared. So once you have this, you can find the expression of the shear stress now. Okay, so the shear stress as a function of y is equal, so the V is the same, the I did not change, so the I can't remember, is 5.813, right? 5.813 times 10 to the power minus 6 multiply by 98 times 10 to the power minus 6 minus 0.08 y squared. And then the thickness, because for this case, we are focusing on the what? On the flange. And we know the thickness is constant at 0.16 meters. So this is divided by 0.16. So you will have the function 90 power 3 divided by 5.813 power minus 6 divided by 0.16 times by 98 power minus 6 is equal to 9.483 times 10 to the power 6 times 10 to the power 6 minus by 7.741 times 10 to the power 9 y squared. Okay. So this is the shear stress distribution equation in the flange, and this equation is only valid from 20 millimeters and up to 35 millimeters. Okay, I'm going to stop here. I'm going to continue again on Tuesday. You will have a quiz posted to you on Tuesday because Monday is a holiday. Okay, if that's the case, have a good long weekend. I'll now see you guys again next week. If you have any question, you can ask me. I'll still be online.